Welcome to the Q&A session 17 from the playlist of friction. The topic is the application of work energy theorem. And today I have taken one question which is written here on this board. And this is the figure which was provided along with the question. So in this arrangement, the block A has got a mass of 1 kg and the block B has got a mass of 2 kg. These two blocks are connected by an inextensible string, by an inextensible and massless string. So we have to find the speed of both these two blocks when this block B has descended downward by 1 meter. So here in this question, the coefficient of friction between the this block A and the surface on which it is kept is equal to 0.2, and this is the frictionless pulley, and these two blocks are connected by a massless and inextensible string. So here, before using the work energy theorem, I will be using the constraint relation, that is the algebraic sum of the product of tension and velocity for this for these two masses will be equal to 0. So for this mass A, this T into V will be taken as minus T into VA, where VA is the velocity of this block A when it is moving in this direction when the block B is going downward. So this minus sign indicates that the direction of the this will be positive because the tension in the string and the displacement of the block is in the same direction. And for this block B, here the tension is in the upward direction, whereas the displacement is in the downward direction. So in this case, the value of this T into V will be taken as negative for this block B. So this will be equal to minus T dot VB, and this will be equal to 0. So from here we can say that the velocity of the block A will be equal to the velocity of the block B. So this is the first relation which I have got. That is, the velocity of A block will be equal to the velocity of the block B. Now I will be using the work energy theorem in order to find the speed of both these two blocks. Now, as per the work energy theorem, the change in the kinetic energy is equal to the sum of the work done by all the forces acting on a system. So here the system is the so in this case the system will be the system of this pulley and these two blocks which are connected to each other by a massless and inextensible string. So here the change in the kinetic energy will be equal, if I take the velocity of VA which is equal to VB as V, then the change in the kinetic energy, that is delta K E, will be equal to half M. MA is the mass of this block A, VA square plus half MB VB square minus 0, because when these two blocks are stationary, then the kinetic energy will be equal to 0. So this is the kinetic energy of this block A and this is the kinetic energy of this block B when they are moving with the velocity VA and VB respectively. But here VA and VB is equal to V. So the change in the kinetic energy will be equal to 1 by 2. Here M1 is equal to 1 kg. So I will be writing here as 1, and this will be equal to, here VA is taken as V. So this is equal to 1 by 2 V square, plus this will be equal to 1 by 2 into the mass of this block B and into V square. So this is the change in the kinetic energy of this system, which consists of two blocks and which is passing over this frictionless pulley. Now we have to find the work done by all the forces which are acting on this system. So here the work will be done. So in this case, the block A is being subjected to the frictional force which is acting in the backward direction. So here in this case, the direction of the force and the direction of the displacement are opposite to each other. So the work done will be taken negative. That is, the work done for the block A will be negative, and for the block B. Now this block B is being subjected to the gravitational force. So the direction of the gravitational force is downward, where the tension is acting in the upward direction. So in this case, the gravitational force is acting in the downward direction, and the displacement is also acting in the downward direction. So in this case, the work done in the case of this block B will be taken as positive. That is, the work done due to the gravitational force will be taken as positive, and the work done due to the this frictional force will be taken as negative. So now the work done due to this frictional force, let us say I am just denoting it as WF, will be equal to mu into N. N is equal to that is mg, and here m is equal to 1 and g is equal to 10. So mu m g into the displacement. Here the displacement is equal to 1 meter. So this is the work done due to the frictional force, and this will be equal to minus 2 newtons. Now the work done due to the gravitational force, because this block B is being subjected to the gravitational force, so the work done here will be taken as positive, because the direction of this gravitational force and the displacement are the same. That is, both are acting in the downward direction. So in this case, the work done will be equal to m into g into h. That is, h is, so here this block B has descended by 1 meter, so this will be equal to, h will be equal to 1, so the work done in this case will be equal to 20 newtons. So the total work done will be equal to 20 minus 2, which is equal to 18 newton, and this will be equal to, now change in the kinetic energy. So this will be 18 will be equal to 1 by 2 v square plus v square. So if I take this v square as common, so I will be getting this as 18 is equal to 3 by 2 v square, and this will be equal to 6. So v square is equal to under root 12. Okay, or we can say that v is equal to 2 root 3 meter per second. So the speed of both these blocks will be equal to 2 root 3 meter per second. And in this question, the most important thing was the application of this work energy theorem along with the constraint relation. So thank you very much for joining this session, and in the next session I will be coming up with a different type of a question, but the topic will remain the same, that is the application of the work energy theorem. So till then, have a nice day. Bye.